Hello, everyone. So once again, we meet to study one of those free response situations that we love so much. And in this case, we are going to study an object that is moving with linear, uniformly accelerated motion. So we're going to look at the displacement, the acceleration, and the velocity of this object. But the basic idea is that this is actually a full-fledged Newton's laws problem because you have a force that is causing the block to accelerate. So let's go look at the description of this and let's see what we can get out of it. It says that you have a block here, and this block has a certain mass m, and so we start by looking at the variables involved. You have a force F1, which is the reason the block is accelerating, and this force is being applied at an angle theta, and because of that, the acceleration of the block is A1. Now, these we can call the parameters. Some people call them the initial conditions of the problem. But basically, the idea is that any algebraic answer that you get has to be in terms of those variables and neither adds and fundamental constants. Now, what do we mean by these fundamental constants? In this context, at this level, the only constant that we have is lowercase g, the acceleration due to gravity. So you can add that to your list of approved variables that you can include in any of your answers, okay? So the next thing that we need to care about is the idea that you want to study forces. And whenever you want to study forces and apply Newton's laws of motion, the very first thing you have to do is a free body diagram. That's very, very important. A free body diagram to tell you what you are expected to consider in this problem. But before you start with the free body diagram, a little advice. Always, in these problems, you never have extra words. These words are very important. For example, they tell you that this block is being pulled along a rough horizontal surface by a constant applied force. All of those things are going to be important, okay? And so whenever we do the free body diagram, we need to start by looking at a representation of the object. In this case, they give you this little rectangle here, and they tell you, draw and label a free body diagram showing all the forces below. It's not only enough that you draw it, you also have to label each force. Now, you want to start probably by giving F1, which is the force applied that makes the object accelerate. And then, because there is a mass and we are near Earth's surface, you have a gravitational force, m times g. And we also have that the object is resting on a horizontal surface. So you have a normal force, Fn. And finally, since the surface is rough, it means that you have to consider friction. And that friction is always going to be against the motion of the object. So reasonably, this block is accelerating to the right, so your friction force is towards the left, and you must also label it. Now, you might include the angle theta in your drawing. You don't really need it, and sometimes they tell you apply only forces to the diagram, so be rather conservative when drawing this free body diagram. Only forces are enough. They don't even want you to draw components here. So that is your free body diagram. Next, they want you to start with your algebraic solutions. Remember that you only can include variables in the approved list. What was this approved list? Well, we have the mass, the force F1, the angle theta, the acceleration A1, and the gravitational acceleration G. Whatever answer we have to include can only have those variables. Anything that is not one of those variables needs to be substituted somehow. So what is the first thing that they request? Well, it says derive an expression for the normal force. So you want an answer that tells you the normal force is equal to something. Well, if you consider that this block is probably accelerating just in the x direction, it means that the net force in the y direction has to be zero according to Newton's first law. There is no acceleration in y, and so the sum of all forces in y has to be zero. From your free body diagram, you have that the normal force is going up, and there is an vertical component, F1y, and then the gravitational force is going down. So this is the equation that you have started with. And the answer that you want is the normal force. So you get that the normal force is equal to gravitational force minus, from trigonometry, you know that the opposite leg of this triangle will be F1 times the sine of the angle. And so that is the answer that you're looking for. Look at the variables involved: mass, g, F1, and the angle. Now, you don't have to have all of them, but you can only have some of them: mass, F1, and the angle, and the gravitational acceleration g. It doesn't matter if you don't have all 5 letters. What matters is that you don't have anything else. So that is your answer for part B. Next, in part C, they want you to include the idea that the object has some acceleration in the x direction. So let's go there, see what we can get. Derive an expression for the coefficient of kinetic friction, mu, between the block and the surface. Well, we already know that the normal force is equal to mg minus F1 sine of theta. Now, the x direction is a little different because they tell you that this object is being pulled and it has an acceleration. So if it has an acceleration, this is an instance of Newton's second law, not Newton's first law. Therefore, the sum of all forces in the x direction is not equal to 0, but it is equal to mass times acceleration a1. Take care that the acceleration is not only a, you have to use exactly the symbol that they give you. So, the forces in the positive and negative x directions are only 2. F1 in the x direction minus force of friction. And this is equal to a mass times a1. And remember that what you are looking for is an expression for mu. And mu appears in the formula for kinetic friction. So what we get is F1 times cosine of the angle, because x is cosine, minus mu times the normal force is equal to mass times a1. Because you want mu, you want to move things around in this equation a little bit. So F1 cosine of theta minus mass times a1 is equal to mu times the normal force. But we do have an expression for normal force because the normal force itself is not in our list of approved variables. So you substitute it by mg minus f1 sine of theta, and so the mu that you are looking for is equal to F1 cosine of theta minus mass A1, all of it divided by mg minus F1 sine of theta. And that is the answer that you were looking for. It only has the list of approved variables: mass, F1, acceleration 1, and the angle. For the next part, they want you to consider the kinematics of this situation. So a little animation to look at it in motion will be advisable. Observe this carefully. So we can see here how the object starts from rest and from an initial position of 0, and then because the velocity is increasing gradually, then the displacement after successive seconds is greater and greater. So the position doesn't change linearly, it always changes quadratically, and the velocity increases linearly because, say, for example, if the velocity was 0 after 1 second, then it's 2 after another second, and then 4, and then 6, and then 8. So the velocity increases linearly, but the position increases quadratically. So as you can see, the idea is that the position of the block is increasing non-linearly, and the velocity of the block is increasing linearly because of the relationships that go as follows. In general, the position is going to include a quadratic relationship with time. You don't need to worry about the initial velocity because it says in the statement that the object started from rest. And it also says that it started from the origin, so you don't need to worry about the initial position. On the other hand, the velocity has a linear relationship with time. And so what you get is that your velocity should be some function that looks linear starting from the origin because the initial velocity was 0, but the position function should be quadratic and starts with the vertex at the origin so that the slope of this is 0 at the beginning, and as time goes by, it slopes up because the graph should be half of a parabola. Take the side of a parabola where the variable is only positive. So those are the kinematic situations to be considered. Now, they want to do an analysis a little more abstract. What will happen if I increase and increase the force applied? Well, let's look at the drawing once again. Consider that originally you had a slightly less than ideal normal force because there is a component of F1 that is going up, F1y. Now, what will happen if F1 is greater and greater and greater? Then you will have less and less normal force. And that means that less and less of the weight of the block is supported by the surface. So in other words, there's going to come a time where if you have enough of F1, you're going to separate the block M from the ground. And that is what's behind the logic of question in part E. If the applied force is large enough, the block will lose contact with the surface. Derive an expression for the magnitude of the greatest acceleration A max that the block can have and still maintain contact with the ground. Well, the idea goes like this. Remember that originally in the x direction you had F1 cosine of the angle minus friction force was equal to m times A1. In the critical situation where your force 1 is large enough and the block is about to lose contact with the ground, the frictional force becomes 0. It disappears. So what you have in that case is that F1 times the cosine of the angle is equal to the mass times this maximum acceleration, the greatest acceleration that you can have. This is like the critical moment where the block is actually losing contact with the surface. And then in the y direction, what you have is that F1 sine of the angle minus mg plus the normal force is supposed to be equal to 0. But if you are at the critical instance where the block is barely losing contact with the ground, then the normal force is becoming 0. And so F1 times sine of the angle becomes equal to mg. So we can combine these two things very productively if you think as follows. Remember that what you want is an expression for A max, the acceleration at that point. So your A max from the x equation becomes F1 cosine of the angle divided by the mass. On the other hand, the mass from your second equation, the y equation, is equal to F1 sine of the angle divided by g. Now, if you substitute this expression for mass into the first equation, what you get is that A max is equal to F1 cosine of the angle divided by F1 sine of the angle over G. Obviously, F1 is going to cancel out. G can be moved around to the numerator, and so A max is going to be equal to G times cosine of the angle over sine of the angle. Now, this is the same as writing G divided by sine of the angle over cosine of the angle. But this is the same as G divided by tangent of your angle. And that would be a nice final answer for A max. So what this means is if you want to know what is the maximum acceleration that you need to barely start separating the block from the ground, all you have to do is divide the gravitational acceleration by the tangent of the angle at which the force is being applied. So, recapitulating, we have studied the forces being exerted on this object. Based on those forces, we can find the expressions for normal force, for coefficient of friction. Then we can say that because the forces are constant, you have a constant acceleration, which determines the linear function for velocity and the quadratic function for position. And finally, we can find critical values for which the system becomes something else. I hope this was useful for you, and I'll see you later.